only one of the mics is working, so no one's going to sound the mic. I'll sort of project. Welcome back, everyone. We understand the first one was a little hairy at the end, just because we didn't anticipate a lot of the installations with problems that we encountered. So we have the course, the series administration, so the event managers like us, the TAs have actually worked out most of the bugs, except for I guess the newest Macro Pro. If you have that, we kind of
or a Dell XPS 13.
Or a Dell XPS 13, then your computer was unsalvageable. In which case, we advise either you directly install it on the OS that you're working with, which would be Mac or Windows, or if you have enough resources, to use VirtualBox like I am doing now. So we apologize in advance that we didn't anticipate this. The few guinea pigs we tried it on, and it finished within like 10 to 20 minutes, and we apologize. And as for Hadoop and Spark, the installation should be pretty smooth. It should be done within 20 minutes. Our Slack at paraproc.com is active, and it will be active for the remaining of the week. So if you have any questions, any problems, and they will creep up, please do not hesitate to ask on Slack.
Yeah, and if you can't get it by right now, it's okay, because this lecture is mainly theory. It won't be a lot of Spark, and we'll stick around afterward to help you get it.
Yeah. That said, we will be having some kind of a demo walkthrough of how to go to the different UIs, different and how to transfer files into the Hadoop system, transfer files onto a Spark. So that we will do. So if you have installed Hadoop and Spark, today is a good opportunity for you to actually try it out. So today, it's actually going to be us two presenting. Mostly the actual difficult part will be more Nolan, but we want to make sure that we're going at a pace that you guys can understand. So we want to make sure if there's a lot of concepts that are being thrown at you and it's pretty difficult, and it is, and it's very hard to understand right away, please raise your hands and ask questions. I will be repeatedly stopping the event and asking whether you guys are following. So if any of you are not understanding what's going on, feel free to bombard us with a lot of questions. All right, so we'll jump straight ahead. It's okay. Never just go. So today we're going to talk about two platforms. Actually one platform, because the other one sits on top of the first one we're going to talk about. It's actually Hadoop. So how many of you here have heard of Hadoop? How many? Cool. So Hadoop is basically the state-of-the-art parallel processing, parallel storage platform. A lot of software sit on it, and we're going to talk about why it's important, what it is. So next slide.
Yeah, so just a basic introduction on what Hadoop is. So it was initially created in Google, and then it slowly evolved into a platform of its own. And it's open source, and so there's a lot of different modules that you can work with through Hadoop, and you can add stuff onto Hadoop. It was made to be able to execute in parallel and store in parallel and manage a lot of data at once. It's used by over half of Fortune 500 companies, so it's kind of like the cool thing right now. And fun fact that the name Hadoop comes from the creator's son, who had a toy elephant named Hadoop.
Because you do. Yeah. You mainly.
So why would you use Hadoop? So again, it's mainly it was created for handling a lot of data at once. So it's really scalable for large processes. It's optimized for high throughput. It's open source, and so again, there's a lot of different ecosystems you can work with. So if you have a specific need or interest that you need to use Hadoop for, there's definitely something that you can use with it. And one of the big things is that it's really good for unstructured data, which would be like a lot of text or a lot of images. So structured data would be like a relational database, which is what usually a lot of different servers work with. But through Hadoop, you don't need a relational database to work with data.
Yeah, so what that means is relational databases basically work with charts and tables. So tables basically is conventional, just a row by column format, and that's sort of what we mean by structured data. And unstructured data can be data in all sorts of forms. Video is just a collection of images, so images, sound, anything that basically is not something that is right away chartable in a table format.
Yeah.
Do we need to explain this? Okay. So okay. So before we actually jump into, do we have large blocks? When is that? It's a large block. Okay.
Yeah, it'll come on there.
Okay. So before we dive in, we already kind of touched upon this, and we won't. I'll explain a little bit. Okay. So we already explained this in the first lecture, but we wanted to make sure that everyone gets what this is. So when we talk about networks, we will say something like a data node or a name node. And what does a node mean? And when I say I'm running a high parallel cluster, what does a cluster mean? So I would like to draw it out. Actually, so we were originally going to show this in two screens, but the screen stopped working. My tuition. All right, so basically, as you can see here, a node basically refers to a point. So all these points here, so these are called nodes. Those of you who are familiar with network graphs will understand what this is. And these lines are called edges, and then together it's a network, right? So in terms of networks, in terms of like computing clusters, this whole thing is a cluster. And each point represents something that takes in input, processes it, and generates output. So your servers and your computers will basically be a node, because what does your computer do? Your computer can connect to other places, receive input, and then do some kind of processing, and then send it somewhere else. So that's an output. So every point here will be a server, and these edges basically are connections between, basically means of communication between the servers. Does that make sense? I don't know. Okay. So together this will be a network cluster. All right, okay. Okay. Right. So before we actually get into also things about Hadoop, I wanted to give you a little sense of what servers kind of look like and what your computers kind of look like. So I'm not going to go into like all the little like what does a CPU look like, what does RAM look like, but I can give you a basic sense of what happens in a server when we talk about a network cluster. So can everybody see when I draw a box like this? Can everyone see this box? Okay, cool. So in a server, basically again we can break it down to about 4 to 6 things. So this is called the I/O. So I/O is basically short for input and output. This is responsible for connecting to receiving input and sending out output. So like I said, a node does these two things. So it handles incoming information and then puts it into the box. And then once some kind of information needs to be transmitted, the I/O is responsible for sending the information out. So this can be a bottleneck of its own, but we're not going to go into that. This is at the I/O. So at the second layer, let's talk about the foundation first. At the foundation lies disk space. So basically your hard drive. So when you think about storage, this disk space corresponds to permanent storage or semi-permanent, so long-term storage. So if you want to save a file and you turn your computer off, everything that's in this space gets stored even if your power cord gets pulled out. So that's basically permanent storage, so disk space. And within here, usually, so there is main memory. So memory is what we usually refer to as RAM. For example, a random access memory. And memory is a lot more volatile. It's also faster to work with and easier to parallelize operations in. So next layer is what we call CPUs. So these are your cores. So central processing units, or your CPUs are working. So whenever you're doing some kind of operation, your mathematical operations, your CPUs will be working on a thing. So the way this works is, let's say you need to process something. what happens is some kind of data is, sorry, and in this, this space lies blocks of data. Okay, that makes sense? So basically when you save your files are stored, chopped up into blocks and stored here. What happens when your CPU wants to work on a certain block is your block, first your disk manager will look for your block, and it finds the block, and then it loads it into memory, and then from your memory it then goes into your CPUs. Does that make sense, everyone? So, you want to talk about the analogy? Or?
Yeah, so basically like a good analogy to think about a server is like think about your refrigerator. So say you want to cook or you want to chop up an onion. So you go into your fridge and you have all those different drawers. And so think of those as your blocks. And so your disk manager is going to look in your fridge, which is your disk space, and all these drawers for an onion. And once you find the onion, you're going to take it out of your disk space or your fridge and then move it to your countertop to chop. And so once it's on the countertop, then you can send out to all your cooks or whatever and have them chop it up.
Does that make sense? So there are two reasons why there's an inherent hardware. Basically, a reason why memory, because of the structure of the memory, it's faster than disk space. But there's also it's closer to the CPU.
Like physically closer.
Yeah. So you gotta remember this. So it'll become an important point later on.
Yeah.
But having your data sets be close to the processors is actually very important. Does that make sense, everyone? Is it everyone understandable? Go ahead. Okay. All right.
So now we're going to start to get into like the actual structure of Hadoop. So we're going to split Hadoop up into two separate functions. It's going to be the storage, how Hadoop stores it, and then also how you process and compute things in Hadoop. And so pretty much throughout this lecture, everything's going to follow this structure. You're going to have like your master or your manager, like the term is master, and think of it like as a boss in a business. And then you'll have your slave nodes right here, and think of these as like lower level employees. And so pretty much anything related to Hadoop will follow this basic structure.
Yeah. So it's good that you remember this structure. It's pretty simple. There's a master and slave. So everything we'll be mentioning a lot of like softwares. And what I mean by software is like an agent inside a program. So each program will be sort of assigned to either a master function or a slave function. And usually a server is designated as a master, and a bunch of servers are designated as slaves. And the manager basically manages the slave nodes. Yeah. Does that make sense? Good. Okay, cool.
So now moving into the actual storage, how Hadoop stores files. So go ahead. So the basic, so how it does, it's basically called HDFS, which is Distributed File System. So basically, Hadoop breaks up your file into large blocks, and then distributes it across your server. And so these so Hadoop breaks them into larger blocks instead of smaller blocks, mainly in relation to this. So when you're trying to, so usually in terms of when you're trying to look up things faster, it's better if you have a smaller block. So say like it's easier if you have a file with 5 people on it, and you're looking for someone named John Doe. It's easier to find them when it's only 5 people. But if you have a file with several John Doe, if you have several files that have 5 people on them and each have a John Doe on them, and you want to count the total John Does, then you got to load up all these files into your memory to work on them. So what Hadoop does, instead of having a file with only 5 people on it, it has everybody in like wherever they're living in one file or larger files. And so when you're trying to find the John Doe, it takes a while to look them up. But when you're trying to count how many John Does you have, it's already all in memory. And so it's easier to split up the counting because all your John Does are already there.
Okay.
Yeah.
Just to make sure this point is understood. So when you are so basically when you're looking for a file or when you're searching through a database, 2 things happen. One is a lookup. So basically, if you think about a traditional magnetic disk, an arm is going around the disk and trying to locate a file location. And then there is the transfer. So once you find the blocks, so once you find it, you transfer, right? Yeah. So smaller block sizes are more optimized, as Nolan said, for quick lookups. You can quickly identify which block it belongs to, search within a small span and quickly transfer out. So that's really good for lookups. But for large blocks is good because less time is spent looking up, but more time is done just having a huge throughput of data. So if you think about it, let's say I want to find a John Doe in California. So that's a very small subset, right? So this is basically like a lookup operation. If you're running a website and you want to get search results like you're searching on the people database on Cornell, then it's a lookup operation. So it may not necessarily be a good idea to have large blocks. But if you want to, let's say, you have a huge data set, like 1 billion rows, and you want to segregate which ones are from California and which ones are not from California. In that case, what you really want to do is process the entire data set, right? And it doesn't really matter how fast you find one point, but it's more relevant for you to be processing a large volume of information at any given time. So that's why you want to have large block sizes, because large block sizes mean you have less lookups, so you don't look up each block as much. You only, for example, if there are 1,000 blocks before you look up 1,000 times. If you have 4 blocks, now you're just looking up 4 times. But the total volume that you're processing at any given moment is actually a lot higher. Does this make sense to everyone? Yeah.
Okay. Yeah, and then also another important thing about HDFS is that it makes a copy of all your blocks and stores it in a different location. So when you're working with servers, you have to work under the assumption that one of your resources is going to fail at one time or another. This adds resiliency to HDFS. So in case one of your, say one node fails and it has data on it, you always have a copy of that data so you don't lose that data and you can continue working. Yep.
Basically, in the Cornell data science servers, a node basically fails like almost once a week.
Yeah.
So like they don't shut down, but they cause some kind of problems. It could be anything. You know, your computer just could malfunction. Maybe they're static. I don't know what it is, but it happens all the time. And you don't want to lose all your operations just because one thing failed.
So like the highlights is that HDFS does large blocks and then also makes copies of your blocks. All right. So
okay.
All right. So now we're going to get into the kind of the architecture of HDFS. So again, so we would have like if you want to pull up the diagram, it's going to follow the master-slave architecture. So you're going to have your name node, which is your master, and so this is kind of like, and he's right here. This is kind of managing everything. It doesn't actually store a lot of data. It just keeps track of all the metadata or where that data is, and it also keeps track of log times, things like that. You have your secondary name node, which is also considered a master, and like every now and then it'll take a snapshot of your master node and store it. And so in case your master node fails, then you just go to your secondary name node and reload the last snapshot. So and then these data nodes, these slaves, they're just storing data. So again, like it's the master managing, keeping track of where all the data pieces are and where all the blocks are, and then the slaves, they're just storing the data.
So
what happens when the name node and the secondary node both of them?
So that's actually a good point. In the Hadoop distributed file system, the name node is actually a weak point. So if your master node fails, like if your master server suddenly like someone pulls a plug, it usually can go down altogether because your head just got cut off. But in industry, this gets mitigated by having multiple name nodes. But it gets a lot complicated when you start introducing a bunch of name nodes. But the function is basically the same. The name node acts as the head, and then basically the secondary name node is like a backup. It doesn't actually replace the name node in any sense. It's not actually a backup. It's not actually a secondary name node at all. All it does is it just maintains a log of where you are. And so, what kind of benefit does that have? One, the name node doesn't have to load everything. Like it doesn't have to go through the entire history when it first loads. Does that make sense? And the second, if the name node should fail, and I don't mean the server, I mean the program should fail, the secondary name node can then say, yo, you were actually at this point. Does that make sense? Oh, I think you have a question.
Yeah, I didn't understand why the data chunks are like bad for lookup or better for checking.
Okay, so this is a good point to go over. Let me break it down again. So let's say I have 4 file blocks versus 2, right? And and my data set is stored in 2 blocks. Makes sense? And I want to find California. So what do I have to do? I have to look up for both these instances twice, right? I'm looking it up twice, and then after I find it within that block, I transfer, right? Versus having it 4 times. So in the in the total amount of time that you spent retrieving that California portion, more of it is spent on lookup in this case than it is here. Does that make sense?
But that's only if you want to organize it. You want to like retrieve one option, then the 4 is better, right?
So having 4 is better, yes. So if you're like just doing a search and you just wanted to get like 1 or 2 things, then it doesn't matter. Like the actual volume of things being passed through the system at any time, it doesn't matter, right? You just want low latency, right? So Hadoop is actually bad for low latency systems. So if you're like running a website and your backend is Hadoop, people are gonna have huge problems. It's not a good idea. But we're talking about data processing in a parallel format. So this is actually pretty good. Does that make sense? Is it clear to everyone? Cool. Okay. So apologize for the switching back and forth, but it's Cornell's fault. or Bill Gates' fault.
Oh yeah, sorry.
For the blocks, are they distributed all within one server or across many servers?
It can be across many.
Okay, and then
So-
the redundancy is just also across many servers? Or?
Yes. Yeah. So there should be redundancies hopefully within servers and outside servers. Does that make sense?
And then one server will hold all the blocks as well, or not necessarily?
That's not necessarily true. It made sure that there are multiple copies of it in multiple locations. So it may not in any sense have everything in one location. Does that make sense?
So you don't have to fit the entire data set on one
But then,
server
if you
necessarily.
think about it, if you were to store like everything in one location, that would kind of defeat the purpose of having a parallel. Does that make sense?
Alright, cool. So now moving on. So HDFS is the storage, and that'll continue like throughout the lecture. So now we're going to move on to how the processing side for Hadoop. So when you're working in Hadoop, you want to be able to parallel the computation. And then you also want to be able to, you have to be able to schedule tasks, like when these tasks will be carried out, or when these lines of code will be carried out, and then who's actually doing it. And you also have to make sure that you have enough resources to do it. So the older version, so initially how it worked, it was all handled by MapReduce1. So scheduling, resource allocation, and computation were all MapReduce1. So like this is not the best solution, but once you understand MapReduce1, it makes understanding Spark and everything after it much easier, and it gives you a lot of you need to know the history behind why Spark exists, and you can learn that through learning MapReduce1.
Just an announcement. Can everyone actually this back and forth is kind of difficult. You can open up your laptops. We posted the slides. So the visuals. Sorry. So we actually separated the text and the visuals, the accompanying visuals, as 2 separate Google slides. So it might be actually useful for you guys to look at the second set of slides. Apologize for the technical difficulty.
Which set is the second set?
I'll send them around.
So it's also you should sign up for paraproc.slack. Did you post it?
No,
Oh, okay. It's being posted now. So 1 second back. Does everyone see it? Yeah. So the slides are designed such that each slide number should correspond to the same slide number here. So there will be some repetitions, but those are done to make sure that these are in sync. So if we're talking on slide 15, your accompaniment slides should also be on slide 15. Yeah, that's good.
Okay. So I think we're on slide 11 right now. So we're on slide 11, and you'll see HDFS. So the storage is your foundation, and then initially MapReduce sat on top of HDFS. Yeah. So now we're going to talk about MapReduce and the basics behind it. So MapReduce is really pretty simple initially. So it's mapping and reducing. So a map function is basically sorting or filtering, and then a reduce function is summarizing that data. So you'll see on
So I know you guys are probably kind of terrified by the
Yeah.
complicated example there, but that's going to be the second example. So the first example, I want to show you a very quick example. So mappers, you can think of, who here uses Python? Most of you, right? So in Python, you have a map function, right? What is a map function? It just
Applies the same function.
applies the same function to an iterable object, right? Does that make sense? So basically, let's say you're sorting, and you have 4 partitions, so 4 blocks of data. So you want to sort concurrently. And what do you need to do? You first assign each of these tasks to a mapper. So each mapper will then work on each partition and sort it. And then the mappers will then have a sorted function. And then the reducers, what the reducers do is consolidate these. So in a sense, mappers do the concurrent tasks. Reducers get the results of the mappers and sort of consolidate the results. So here's a reduced result. And then there will be another reducer here, basically consolidating the results of these two. And then you'll have a final sorted version. Does this make sense to everyone? So this is the basics of MapReduce. There's a mapper that does concurrent parallelized jobs, and reducers that consolidate these results together to get a final result. Yeah, that good? And we're going to actually explain this process of sending from mappers to reducers in more detail. It's a very complicated process. But if you look at the examples here,
so I just want to walk you through what you're seeing right now. So like so this is basically, you want to find the word count for everything in one big file. And so this is your starting file. And so what MapReduce does initially is it's going to split up these lines onto each partition or whatever. And then once you're on your partition, you're going to run the map function. And in this case, the map function is just going to be giving a key and a value to each word. So after it's split, you're going to give a key and value to each word. So it gives apple the value 1, because there's only one apple, and orange the value 1, mango the value 1. And it does this across all nodes. And then this is where all the magic happens. So this is the MapReduce shuffle. So basically, kind of in like a hand-wavy way to explain it, it's going to collect all the data, sort it, and then put all similar keys onto one node. And so now that they're all on one node, the reduce happens. So it's going to count. It's going to sum up these values into one value right here, and then your final output, again, one last reduce into your final word count right here.
Does it make sense? You guys should ask questions if this is in any way confusing.
Don't worry about the shuffle for now, because we're going to explain that in more depth later. So yeah, but basically you're mapping, so you're applying a function, and then it sorts, and then reducing.
Yeah. So
So like the mapping and everything is done in parallel, right? So then,
correct. Yeah. So you're mapping to like all your separate workers. Yeah.
And then after the shuffle, is it also like ever parallelized, or is that always like them?
So that's the key we're going to get into a little bit. The shuffle is hard to parallelize because everything's in different places.
Yeah.
But after you shuffle and send it out again, then it's in parallel again.
So basically, in your system, you have 2 types of. So you have CPUs, right? So let's say you have 50 CPUs. Some of them will be designated as mappers, and a lot fewer of them will be designated as reducers, because obviously they'll be parallelizing, and then some of them will be reducing, right? Does that make sense? So the reducers, there will be more than one reducer. So in a sense, the reduction also happens in parallel. Does that make sense? Okay, so this part is actually the very important part. So I'll explain the MapReduce shuffle. The concept of it is actually fairly simple, but it's just in actual as an actual problem, it's difficult. So the MapReduce shuffle basically refers to the transfer of tasks from mappers to reducers. So if you have like 100 mappers, and they all, so basically when you're doing a count or you're doing some kind of sorting operation, what are you, basically you're assuming that your mappers will finish somewhere close to each other, right? And basically when mappers are done, their intermediate results are then sent to reducers. Does that make sense? So that is actually a scheduling problem, because one, if you think about it, Okay, so one, it's the data transfer is fastest within a node, right? Because all the CPUs are connected by memory. So memory, it's really, really fast to transfer information from one CPU in a server to another CPU in a server. But it's really, so let's say I have 2 servers. And let's say I have one reducer here and another reducer here. Let's say I have one mapper that just got finished. Let's say I just finished a task. Not everyone else is still working, but one task is still mapping, just finished mapping. So what do? So let's say I have one reducer, but there's like, this reducer is still working. What are the 2 choices, I wanted to throw it out on you guys. What are the 2 choices that this mapper can do? And let's say this one is free. What are the 2 choices that are?
Send it to the other reducer.
Okay, that's one choice. What's the other one? Wait, right? So basically you're weighing the probability or the amount of time that will probabilistically wait to have the reducer get freed up against the time that you require to send to this server and then put it on this reducer. Does that make sense? So in a sense, this is a probabilistic modeling. You have to weigh when this is going to open up versus when how much time you're going to probably take. And that's also a probabilistic thing, right? Like the amount of the data transfer rate may not be stable. It may take some time that's variable. Is that okay?
Yeah.
Is that good?
And the main takeaway here is that this process, the shuffle, is going to be inherently the slowest part of your MapReduce. Because there's going to be a lot of input, output, reading, and writing. And that's just inherently slow because you're moving things from memory back to your disk and then back out.
Yeah. So, so Nolan just pointed out an important point. So whenever a mapper sends information to a reducer, a mapper must back it up on disk. Does that make sense? So I drew that diagram earlier. They always have to back up the file on disk because what if it fails mid-transmission? You know, your intermediate results are all just lost. So the MapReduce shuffle is very costly because you're writing a lot of temporary intermediate files onto disk. Does that make sense, everyone? Yeah. And also a lot of reads because the reducer then has to also read it in. Okay. Yeah. So please remember, this is by far the costliest procedure in all of parallel processing, and we'll see why that matters. Okay.
All right. So again, we're going to go deeper into the MapReduce architecture. So again, you got your master-slave architecture. So your job tracker is again like your boss. He's scheduling all his employees on what jobs they need to do, and it's splitting up the jobs amongst all his employees. And then you have your task tracker, which is your slave, and so this is basically the lower level employees completing these tasks. And every now and then they communicate to monitor the status of the task.
Does everyone understand the diagram? Right? Cool? Yeah. So I'm going to keep asking you guys if you, just because we don't have it on screen.
So MapReduce was the older version of computation. And so the newer version, instead of having one thing handle the allocation of resources and the scheduling of tasks and the execution of tasks, the newer version has it split up. So the scheduling and allocation is now handled by something called Yarn, which is literally just called yet another resource negotiator.
You're clearly not in a good mood.
And then, so the scheduling and allocation is moved to Yarn, and then the computation of all your code is now handled by a separate software that can sit on top of Yarn, which is sitting on top of HDFS. And so in this case, for this lecture, Spark is that computation framework sitting on top of Yarn. So why did they move to this newer version, and what makes it better than MapReduce? So as we said, MapReduce is pretty slow compared to Spark because after every map and reduce function, like Daewon said, it has to write to disk, and that's pretty slow. That's inherently slow. The newer method, Spark, does a lot more. It keeps a lot more in memory, so it's writing to disk less often. So this allows Spark to parallelize a lot more operations because it has a lot more things in memory, and then also since it's writing less, it becomes a lot faster.
So also we weren't didn't put it here, but like it's really important to understand that in MapReduce, all mappers are sort of working independently.
Yeah.
So there's no master plan of how to run these mappers as efficiently as possible. It's just when they're done, a shuffle happens. Like whenever a mapper is done, the system sort of looks at it and then says, okay, just write to the disk and solve some kind of probabilistic model, and then either send it to another CPU inside the server or send it somewhere else. So that's all that happened. But in Spark, we're going to discuss very specific optimization methods that Spark uses to make the plans a lot faster. But Spark basically optimizes the plan first so that the number of times the MapReduce shuffle occurs is fewer. Does that make sense, everyone? Okay.
Alright, so now for Yarn. So again, this is the scheduler of the newer version. So this is going to handle all allocation and scheduling of resources. So again, you have your master, your resource manager. So it's handling what resources you use where, but it doesn't monitor the tasks. And then you have, so this is kind of a new concept, the application master. So now you can have a middleman or like a secondary master almost. And so every time you have a big chunk of code or an application master is created. And so for that big chunk of code, it's going to monitor all the jobs and all the applications till it finishes. And it's communicating constantly with the resource manager. And then this master is handling all of your lower level employees or your slaves. So it's just going to monitor, and all these lower level slaves are just monitoring the status of the nodes.
Does that make sense? You just said a lot of things.
Yeah.
So does anyone understand why we say task or chunk of code? So what's actually interesting is it's not always just the data that gets transferred. So once I'm done with like a part of a CSV, maybe maybe the thing to do is not to send that CSV file, which is a large file, but actually get the code that needs to happen right after. So sometimes in the network, the things that are being sent and received are not just data files, but also code that needs to happen. Make sense? Cool. And so the diagrams that we have on the other slides should be a lot more explanatory. But basically, Yarn is just the scheduler. So before in MapReduce did scheduling, allocation of resources, and also parallel processing. But now Yarn is, so Hadoop, whenever we say Hadoop, it's only the storage and the schedule. It doesn't actually do any parallel processing. Does that make sense? It's just like a really good platform to do parallel processing.
So yeah, now we're going to get into, so we've talked about the storage, we've talked about the allocation of resources. Now we're going to talk about how all the computations, and the particular framework we're going to be talking about is Spark. So what is Spark? It's just the framework that sits on top of everything, and it's 10 to 100 times faster than MapReduce. It's really cool because there's several APIs. You can work with Spark through Java, Scala, Python, R. And it's able to sit on a whole bunch of different things. If you don't want to work with HDFS, you can work with a lot of different things. And someone from some newspaper called it the Taylor Swift of data science, because it's like relatively new and it's a superstar.
Yeah. So like if you think about it, so Spark is the only open source software to have beaten a supercomputer with the same number of cores. So Apache Spark really is one of the leading softwares in sort of the industry today. And originally Spark is actually written in a code called Scala. So Scala is a new type of object-oriented programming language. And it has basically a bunch of APIs that can translate Scala code to Python, R, and SQL. And basically the one that we're going to focus on for this series is PySpark. So it's going to be the Python API to interact with this. Okay. Yeah.
Alright, so now we're going to get into the Spark architecture. And so it's kind of a lot again, so we'll go bit by bit. Okay, so the master is called your driver. And so you should, on your slides, you should see a pretty simple visualization of this. So you have your master, so it's like the entry point for Spark. It's going to take your chunk of code and then split it amongst several tasks and then schedule those tasks. And it's also going to negotiate with your cluster manager. And so your cluster manager in this case would be Yarn, because it's sitting on top of Yarn.
But it's also important to understand that it can be anything. It doesn't have to be Yarn.
Yeah.
So Spark actually has a standalone mode. So like Spark can work on its own without Hadoop at all. We're not going to talk about that in this series. We're interested in working on with Spark in a Hadoop system. And for a standalone mode, though, they use their own scheduler. So whatever scheduler is being used, it's for Spark is the cluster manager. Does everybody understand when we say data partitions? Partitions? So the blocks that I talked about, they're basically partitions, right? Basically, when you get a huge data set, Hadoop, for example, just chops it up into a bunch of partitions, makes a bunch of copies of partitions to make sure the redundancies exist, and then stores it across different locations. So when we say partition, that's what we're doing. Okay. Next one.
Okay, so again, your cluster manager is like another master. So again, it's just going to be Yarn, and so this will take care of all your resources. So Spark doesn't really handle the resource allocation or how you're going to use your resources. And then again, you have executors, which are just low-level employees performing all your processing tasks. Yeah.
Any questions? Yep.
What was the application that you mentioned?
Oh, the application. Okay, so it will be a little bit more easier to understand when I actually show you the application master. But basically, application master is the middleman, just or middlewoman.
Yeah, just think of it like as a contractor. So like you get a job, and then you're gonna hire someone to manage that job for you until it's done, and then.
Yeah.
So basically, the application manager in Yarn is the one which is actually determining what processes is going to take place in what way, and Spark is just processing the entire plan.
Actually, you're missing that. So application master actually exists between Yarn and the Spark program. But in a sense, it's like a liaison. It's just basically it just optimizes the negotiation of resources. So when I say the negotiation, it sounds like two people are sitting at a table and I want 2 more cores. No, you can't. You got one. Like it doesn't happen like that. It's just they're just solving problems. So it's like another program just solving problems. So it's solving a mathematical problem to make sure that the resources that are being allocated by Yarn to Spark is being optimized. Does that make sense? But I actually like the other negotiation guys. Come on, man. Let's get more memory. All right. So RDs.
So Spark still has to think about data in a particular form, and so the way it abstracts data to work with it is called an RDD. So it stands for Resilient Distributed Data Set. So it's pretty self-explanatory. Resilient because it's immutable. Distributed because it's spread across the cluster, and then the data set. So it's partitions of data stored in memory. And so with an RDD, it's just like a basic object stored in memory. But again, so Spark is kind of in like a transitionary phase right now. So RDDs have been around for kind of since Spark was around. But there's been a new abstraction of data that's actually more optimal than Spark that we'll get into.
But that said, it does not mean you should ignore RDDs completely. For the second type we're going to talk about actually uses a lot of the RDD functionalities. And since RDDs have been around for so long, or have been around for a relatively longer amount of time, a lot of the functionalities that it offers is there are a lot more functions that you can use. So keep in mind that RDDs are useful.
Okay, so sticking with RDDs, so the way that Spark schedules these abstractions is through a DAG, which in case you haven't taken,
Switch over?
or you can just draw it. Okay, so a DAG is basically a directed acyclic graph.
So, who knows that? Oh my God.
So basically like it's directed because there's a direction to these connections. It's acyclic because you can't start at one node and then find a way to get back to it. So there's no cycles in the graph.
Yeah.
And then it's a graph.
Yeah, so like if you understand, so this is very applicable to data processing because you have a result, right? You have a starting input and then an output, and you don't want to come back to the same point you were. And basically it uses this data structure to optimize the processes that you're trying to parallelize. So let's go back.
Yeah, so how does it actually use a DAG? So when a command is submitted to Spark, it's going to take all the things that you need to do and turn it and produce a DAG schedule. So we'll get into like the specifics of that in a second. So the main advantage of a DAG schedule, so with traditional MR, MapReduce, we mentioned this earlier, it only knows about one map and reduce function at one time. It doesn't have an awareness of all the MapReduce functions you want to run. When you have a DAG scheduler, it knows all the map and reduce functions you have at one time, and then it says like, oh, all these map functions can be run at the same time because they don't depend on the same resource, and so for the same data, and so it can run all these map functions at once in parallel and then write to disk instead of running one map function, writing to disk, reducing, another map function, writing to disk, reducing. It runs like 5 map functions, then it writes to disk, and then it does it again. So basically it's less of the shuffle. So since you're shuffling the data less, it's going to be inherently faster.
So does that make sense, guys? This is a very difficult concept.
So
like,
yeah, we have a visual.
Yeah, we have a visual to. It's okay. I think we already. Okay. Oh.
I mean, no, I meant like.
Yeah. So for example, so these are all map functions that you want to run. So what the DAG will do, so as you see, it's like a directed acyclic graph. So the nodes are your RDDs, and so basically what the schedule will do, will say all of these RDDs can be run at once and in memory. And so it takes all these RDDs and all these operations and puts them in memory and operates on them. And then after you do all that, you write to shuffle, or you'll shuffle the RDDs. With a MapReduce, it'll have to do this RDD, map it, and then shuffle, and then this one, and then map it, shuffle, and then like that. So it's just less shuffles.
So basically, to put it in other words, Spark first solves the DAG problem. So it creates a tree. So it creates a bunch of like a directed acyclic graph. It creates a directed acyclic graph, and what it does is it tries to find places, a large section of it that does not require shuffles. So it tries to group things together, and then it tries to shuffle as the least number of times. Does that make sense? Yeah. So that's basically basically it, I guess. What else? Do you want to talk about the redundancies, or like, for example, the data being... So, for example, an example is like, let's say you have 4 mappers. If 4 mappers require the same piece of data, you can't run them concurrently, right? Does that make sense? Or like if one CPU is working on a piece of data, and all 4 require the same piece of data, we can't parallelize this. We gotta wait for the one to finish, then the next one, then the next one, then the next one. But if they're working on different pieces of data, or can be positioned as in such a way, then you can parallelize the mappers, and then you can wait for all of them to finish before shuffle, right? Rather than doing it doing one core, then shuffle, then one core, then shuffle, then one core, then shuffle. So that doesn't happen. So in a sense, those mappers that I just mentioned can be grouped into one process before doing the shuffle. Okay. So and it's worth a little bit of wait for having all these finished and doing it the MapReduce shuffle once, rather than having them do all the MapReduce shuffle like 4 times. That's clear? If you have any questions about the diagram, and if it's like we've already like progressed like 4 slides forward, if it doesn't make sense, please stop us, because this is a lot of information. This is like basically a semester of us learning on a computer with like a bunch of failures all the time, and just presenting.
So the new abstraction that I mentioned earlier is called a data frame. So just think of a data frame as in like your R data frame. So instead of just objects, a collection of objects like an RDD, data frames are a collection of something called row objects. And since it's a row object, you can make a table out of it. And so whenever you query something, an RDD, you don't have any idea of its structure, and so there's no way to optimize it. But when you have something organized into a table or a data frame, when you're going to run your queries, you can optimize that process. And so these are faster, and usually these are faster than RDDs, because on top of the DAG scheduler, it also has a query optimizer. And so it makes it even more faster than RDD.
Yeah. So I can talk. So I can talk a little bit about query optimization, but before that, are people familiar with data frames? Data frames? Okay, so data frames are basically the same thing they're kind of just a conventional chart format. So the rows are different data points, and the columns are what? Like fields, right? These are just categories. And what could be an advantage of having this kind of structure? So what is an advantage of having columns assigned? Any ideas? Yep.
Iterate by columns, I guess.
What by columns?
You can you just iterate by columns.
Yeah. So sure, maybe you can iterate by columns, but you got to understand these are actually all row objects. So they can be grouped together using and find the columns values together, but you got to understand these are row objects, and it's necessary because usually a data set can only be parallelized in rows, right? Their equivalent objects are the rows. Yeah.
It makes locating objects easier.
Actually, yeah, sure. Like for example, maybe if I need to do one condition, I can check the single column, and I can. What are some other? Yeah.
I mean, if you have to do like a certain operation at every row, you can just easily pull out the row because you know that it's the collection of rows pretty much.
Yeah, sure. Okay, so I think that works too. So if you know the column names, so has anyone here taken a database class? No? Okay, so in database class we learn about like query optimization. So let's say I am joining two tables, right? And the final, so if you're joining two tables to create a final table, so let's say I want to know, so this is a table that has three columns, the name, height, I don't know why this matters, but let's say weight. And this is name and what? Major, sure. And you want a final table with name, just because it's a unique identifier for some reason, and height and major. So usually what happens in a join, for example, is each row is paired with every row in the second table. So if this has m rows, and this has n rows, you have m times n objects, and then once that happens, you filter them out by ones that have the same name. Does that make sense? So like in a join, you have to do an m times n operation with like all the columns. But if you know the columns in advance and you know which columns matter, you could technically drop a column that, okay, it says height and major. You could drop the weight column, not even look at it, and just process these, right? So you basically just reduce the number of columns you have to worry about by a fifth. So that kind of optimization can happen even before. So even if I don't know anything about this data set, but I know the final one has height and major column, do I need to worry about the weight column here at all? No, right? So that's kind of like an optimization that you can do, even like besides even the DAG problem. This is a query optimization that you can do if you know your data set, it can be organized into columns. That make sense? Yeah. Cool.
Yeah, so just like in summary of why Spark is better. So again, it's much fewer shuffles to handle. So like going back to like the onion analogy. So say you have your onion in your fridge and you want to cut it up into 4 slices.
And the cook can do only one cut at a time.
Yeah.
Like it's one, and then you have to do it twice.
And so if you were a MapReduce cook, you would take out the onion, you chop it up, and put it back in the fridge. And then go through the fridge again, take out the onion again, chop it up, and go back into the fridge. So you could only do 1 slice at a time before you have to put it back in the fridge. If you were a Spark cook, you would take out the onion and hack it to pieces with one thing.
Yeah, like also, because the counter is closer than the fridge. And everything happens on the counter.
And then your fridge is full and you gotta sort through your fridge.
Does that make sense? Does everyone understand? It's also the reason why we have like one of the slides for the company side, a picture of the fridge.
Yeah.
We want to like put the fridge up.
Okay.
But
yeah, and then another reason Spark is better is when you're using data frames, your queries are optimized, and then in general, all your operations are optimized before they're put in parallel. And then again, it's the idea that you're doing everything like on your kitchen counter instead of having to work in your fridge.
yeah, so like quick, the data frame is actually quite a good way to optimize, because this is just the join operation that I just did. Like dropping columns is just one way of optimizing queries. You can even for a join, which table gets joined on which table, like the order of these tables actually matter too. So there's like a whole set of query optimization that can happen that can speed up the process, and this is part of the reason why it's much faster with data frame.
Just say how would you join that, because there's different dimensions. You have subcategories where like.
Yeah. So in this case, we're joining on a name. So I just made the qualifying statement that the names are somehow a unique identifier, although it's probably not. Like each name uniquely identifies a row. In that case, you can join the two together if they have different.
But some data points will be empty, right? Because there's any.
Oh, yes, you're correct. Yeah. So some, or it could be the case that this is just like a mapping. Right? If you have this name, then you have this name. So it can, by theory, have a smaller second table, but be able to output things that have non-labels. Does that make sense? So we're gonna jump into demo right after, but I want to make sure everyone understood everything in the presentation before we jump into the demo. Do you guys have any questions about MapReduce shuffles or data frames or the history of data frames or anything that you would like to know, and we will be happy to answer. Yep.
Would you mind going over DAG a bit more?
Okay. Yes. Good point.
Yeah. So what are you confused about?
Mostly how it's grouping stuff.
Okay. Oh, wait. Do you want to look at the diagram?
Yeah. Sure. So you can make that. Sparky rock or.
Oh, okay.
So sorry. Back to the diagram. So let's say all of these. All of these maps don't depend on. So say for example you have a text file, or you have multiple text files, and you want to run mapping across all your text files. And say you want to map map a key to each word, like we did earlier. So initially in MapReduce, you would go to one of your text file, map that, then write it, and then go to another text file, map that. So what DAG does is it recognizes that you can do the same map function in several map functions on your different text files without having to write to your memory. And so basically it's saying, let's do all these map functions across these unrelated text files and then write to memory. So it's basically, it's like a more general awareness of what your grander scheme and what your grander goal is, and then optimizing based on that.
Also, if I may add, if you think about it, so in a way, this is an optimization that's very good, just because the MapReduce shuffle is such a bad operation.
Yeah.
Like if it would make sense, like for example, if you have 4 mappers, then maybe it's like just best to just do a shuffle every time one finishes, right? If the MapReduce shuffle was a fast operation, but because the MapReduce shuffle is like the overwhelming bottleneck of all the parallel processing time, this is basically trying to find common places that can be grouped before doing the MapReduce shuffle. So in a sense, it doesn't feel optimal, but just because the MapReduce shuffle is such a bad, like, time-consuming operation, this in the end, this is actually a smarter way to do data engineering.
Yeah. So like in the onion analogy, like the DAG would recognize that you can chop your onion 4 times once while it's on the counter instead of having to keep shuffling in and out.
Yeah. So it's you'll see like basically the way we progress through like MapReduce 1 to like Yarn to like Spark and to like data frames, it's all basically like more and more awareness of the actual operation and optimizing towards that operation rather than like making it like I mentioned embarrassingly parallel last time. These things aren't embarrassingly parallel. Like some things have to happen in sequence, and when things happen in sequence, you have to do a shuffle, and we want to reduce the number of shuffles. Oh, I think I saw a question. Yep.
With the onion thing, what goes into the DAG? So like chop once, then like how do you map that? Like.
So, yeah. So like which basically it's more like which process happens. Like one cook chops this. Okay. So and that happens, and those are like the nodes. and then each time a chop happens, it's like an arrow.
Yeah.
And then you find which ones can be grouped together before the onions can be all shuffled around. Does that make sense?
Sure.
Like basically, in some sense, there will be a queue kind of waiting to like wait to have all the other ones finished. Oh, I heard a phone dying. Okay, so basically, like this is kind of like the idea. Like if one cook finishes, and let's say 2 cooks are free, and I just finished, I could immediately pass it off to Nolan. But the only way I can do that is to first put it in the fridge, right?
That doesn't make sense. Like
It doesn't make sense for everyone to do that. If we can all put in the fridge all at once. If the operations could be grouped together. Does that make sense? I don't even know why we pick the onion analogy, but it's happening. We're gonna push for this, like onions, like 2 cuts for onions. Okay, but these are all really good questions though. Anything else?
So the MapReduce writes to the disk every time. In this case, you're just reducing the number of disks, right?
exactly.
Yeah. So it would be wrong to say that Spark does entirely in memory. It doesn't. So every time the MapReduce shuffle happens, due to the necessities of memory just dies a lot. It just becomes volatile. So you have to back it up sometimes. So we're just reducing the number of disks. Yeah, that's correct. There's a whole a range of research going on how to even not have anything to do with disk space at all, which would actually speed things up. But for now, it's being so another consideration that Spark is making by doing MapReduce shuffle is that memory is expensive. Memory is like really, really expensive, so it's usually easier to work with disk. But in the future, if memory prices go a lot less, becomes a lot smaller, then another software that doesn't rely on disk space at all will emerge, and it will probably be like an updated version of Spark. So until that happens, Spark will be sort of the leading software in the industry, and it will be for a long time, actually. So, any other questions or yeah?
So how is this related to the graph?
So like this would be like so.
This is a graph.
Yeah.
How is this graph? So the directed
Yeah. So wait, go back. So all these arrows are directed. They have a direction, and you can't come back to one node once you've left it, right? This is a very simplistic DAG. Does that make sense? Like this is a DAG, right?
Yeah, I know that, but how do I enter the directed? I've seen in the other graph they are directed to each other, but this one is just.
Yeah. So this would be like a really.
This is a very simple example because like in word count, all you need to do is like each block just needs to count things, right?
And like the one you saw earlier, like your Spark DAG would never look that complicated. Like go, Cameron, go. So like that, like your DAG is never gonna look like this. Usually it's just like this to this to this. Yeah.
So this was just to give you an idea of what DAGs are, but in reality, the DAG that Spark solves will never be this complicated.
Yeah. If you want to, we could show like what the DAG actually looks like.
Yeah, sure. So, I'm gonna jump into a demo, and I've already started a Spark process. Okay. This has died. So, what these all mean, these commands mean, we will go into in the next event on Friday. So on Friday, what we'll be teaching is basically how to work with Spark. Specifically, like these are all sort of configurations that I'm passing on to Spark before it is launching. So I'm telling it to launch in a certain fashion. And once you actually launch in a certain fashion, we'll talk about how we'll actually implement the actual Spark code and how you write your Spark code can influence your specific performance for that task. Make sense? So I'm just gonna, for now, I'm just gonna say what it is. For PySpark, I told it to launch using Yarn, so it's gonna use the Hadoop infrastructure. It has, it's deploying in Node client. I'm not gonna go into that. I'm gonna go into that more next time. It has number of executors 60. So this is obviously not my laptop. I have a 60. I have 72 cores at my in my arsenal right now because this is the server. This is the CDS servers. I'm using 60. I can also tweak how much memory I can use, and I can tell it to use a certain scheduling mode. And I'll go into this mode, but basically I'm telling it to do first in, first out. Okay. And so, my Spark contest or my Spark session has now started. This Jupyter notebook doesn't actually matter. The content of this Jupyter notebook doesn't really matter right now. I will teach you how to write this next time. But you can check whether this is running properly on several channels. So first of all, if you are running Hadoop, so has everyone installed by any chance? Most of you have? Okay, so if your Hadoop session has started and is running fine, this should be able to pop up if you use the port 50070. And we'll post these port numbers. But basically you can, for example, can everyone see the actual text? It tells me what mode it's in, how much of the database is used, what's the configured capacity. So we actually are very small. We have 50 gigabytes of capacity on the entire server. We can see how much of it is being used. For example, you can actually go to utilities. So can everybody start running their Hadoop? So for those of you who have it, this is a deprecated command that Cameron really doesn't like. But there's a start-dfs.sh and start-yarn.sh, right? You can actually do start all.sh and do them all at once. For some reason it's deprecated, but this works too. Okay, I don't have it in my version, so I don't have it. But does this all work for you guys? Okay. If you already have Hadoop running, then doing this will not be good. It will try to do it again and be like, there are things already running. What are you doing? Okay. Is everyone running Hadoop?
Yeah.
Okay. So if you're right, okay, actually.
They want.
It says load manager running is process and for 90 first.
Yeah, so you already have things running. Exactly. But this is a good use case. Okay, so I'm gonna just I'm gonna stop everything. I'm gonna kill everything. I'm gonna start from scratch. I realize I kind of started too fast. So right now I'm with the actual person responsible for the servers sitting in the front row. I'm basically just fiddling with the servers as I want, but apologies. Everything has died now in the servers. You can see the process is just being killed. So if anyone was running Spark before, it's sorry. It's okay. No one's running.
Is this the server like?
Yeah, this is the CDS server. This is like our jewel and pride. And it's also sometimes just crashed on its own. That's good. Okay. Also, in general, if it's a warning, you're fine. If it's an error, something's bad. If it's a warning, then you're good. Like if something is working, at least function, it's fine. Don't question it. It's just with Spark and Hadoop, it's basically it's a system made to expect failure. So it will happen. Okay. All right, I just started it. So there are several ways you can upload files, but follow me. So let's create a file called Hadoop demo by typing. Okay, let's actually do VI. Some of you don't have to. You'll have this. Press I, and then you'll be able to start writing. And then press.
It says there's no demo.
Yeah.
I think it says could not find or load bit plus demo.
Oh wait, what? So VI Hadoop
Oh.
demo. crazy. Okay? Doesn't really matter what this context is. We're just trying to make a file. If you don't type anything and then exit this, you'll actually not create a file. The file will be automatically deleted. So we're going to press ESC. So we're actually going to go over the basics of how to do this last class. And then the last class we kind of installed the Fuji. So for the whole class. So press ESC, press Shift, ZZ. W key, you can't go out there.
Wait, so you're
I use WQ.
It's WQ. Hit colon W to save and then Q to exit.
Or just do Shift ZZ. Works fine.
This easy technically works.
Does everyone come back to this? Is everyone come back to the original terminal? That good?
How do we quit? How do we get out of this?
Colon
Colon WQ.
Escape. WQ.
Escape, colon WQ. So like this, and I'm in here, right? And then when I press I can write something. Press ESC, colon WQ. And then, please remember to press enter.
Colon, then a letter W.
W and Q. Alright guys, okay, so there are several, so if you do ls, you should have a file called Hadoop demo, right? Does that make sense? So on your computer, on your browser, do localhost colon 50070. So like type localhost 50070, okay? For me it's going to be different, but I'm just going to do master. Does everyone get this UI? Is your Hadoop running? Did you do JPS and it has a name node? Okay, that's we'll have to do some CPR on UGs, but does everyone else have their this
Wait, do I have to run the PySpark command or do I just do start all?
start all?
I already did start all.
Wait, so does everybody see this?
What was the port number?
50070. So you're gonna have to do localhost the colon 50070. Did you get that? I need a nod if you guys see this. Nod. Nod. If you nod, like. Okay. Okay. So go to utility and browse the file system. Like right now I have a bunch of stuff, but I shouldn't have you guys shouldn't have anything here. Right? Does that make sense? So I'm gonna go back and do Hadoop fs dash. So I'm basically telling Hadoop, you'll go to your file system, and dash is the thing that the command I'm gonna run. I'm gonna say, okay, create Nolan / Nolan, or whatever your name is. Put it there, and it will, create the folder. So go back to your UI, press refresh. So your UI does not automatically refresh. So you have to press F5 all the time. Now I have a folder called Nolan. Does that make sense? Hadoop fs dash mkdir, and that's. Is that good? Everyone with me so far?
No.
Okay, if you have questions, raise your hand and be like, this is cool. Yeah? Is it a warning? Is it a?
I pressed it to and then pressed enter.
Wait, Nolan, can I have your mic? Can I have your mic? I think you turned it off. Okay. All right. Everyone with me so far? Okay. Hello? Hey, everyone? Everyone with me? So if you create a folder using the -mk here directory, so make directory basically, that's what it stands for. I have now created a no-one directory, right? I can click there and then there's nothing, right? There's nothing in here. Is that everyone understand this? Okay, you guys have to like frantically nod at me so I know. Okay, so someone just calmly nod at that. Okay, so the next thing I'm gonna do is, I have this Hadoop demo thing that I created, right? They won't get off my server. Yes, that works too. Whoever did this has a huge ego because it's actually our server, and he said no. I think it might be Ryan. No. Okay, so I'm gonna do this. Hadoop, fs, and then what I'm gonna do is put. So I'm gonna put my local file into the Hadoop folder. So I want to put, the first thing that goes is the file I want to put it in, and then the destination is the Hadoop distributed file system URL, which is NOLA. And it just finished.
So we put our thing, right?
Do whatever you need.
Whatever you call the thing.
Whatever you call the thing.
Yeah.
Just be like, I don't know, say DAG or something, or like data frame. Just to review stuff. Is that, everyone done that? Cool? Like thumbs up, everyone, yes? Okay, cool. Okay, so what you should see now, if I refresh this, is this file. And it tells me the permission of the file, as a name node should know the permission of every file in this folder. It knows the owner, which in this case is HT user 1. It has a supergroup, I guess. Ryan, you changed this last time? No, whatever. And give you the size. Like, obviously, I just wrote one line, so it's 69 bytes.
Depends on how much you.
Depends on
Because you type nothing, basically.
What is supergroup mean?
this is a Linux thing that will not go into. But there's one there. I know, but it's we don't want to go into it. Yeah. Yeah. Okay. Okay. So you guys can play around with that. So next one. Next one you can check is the same like URL, so localhost : but instead of a 50070, type 8088. Does everyone see this? With like 4 cores. If yours says 132, something wrong. Okay, does everyone see this? Cool? Okay. What was that? I mean, it says memory reserved, V cores used, V cores. It says 0? Okay, V cores used is 0. V cores total, what is it? 8. You're good.
Oh, that's the cores of yours.
It's different. It's different from the actual. Means your yarn is not working. So come talk to us after. Or talk. Okay, so everyone sees this, right? Everyone sees this? Okay, so now we're gonna go back to PySpark. I just ran the PySpark command. You guys should know basically PySpark. You can stop at deploy mode client for you guys. Like all this other stuff you can, if you want to copy, you can copy, but basically you can run this.
If you copy, then fuck us.
Oh yeah.
Don't
Actually no, if you run this, the computer will be like, nah, I don't have 100. I'll just do like 2. Like it will just cap it. Like your yarn actually enforces some limits as to what. Yeah. So don't worry, even if you screw up the numbers here, your computer will not crash. There are safeguards. Probably. In all likelihood, they care about your last one. So. So the thing about this is when you started a PySpark this way, so we've linked our PySpark commands to the Jupyter notebook so that whenever you run PySpark, it automatically generates Jupyter. And that means a Spark session will start as soon as you actually open up a Jupyter notebook. Does that make sense? So if you guys do new, and then here you have Julia as well. But like press this, it will like open up a new notebook. Is that true for everyone? And if you open up a new notebook, and for me, I'm gonna open up my demo. It's gonna take a while, but if you go to the other 8088 port and F5, it will take a little bit. Also, check your terminal, and it says, see how it says warn? It is warning you. It doesn't mean anything. Okay? It's like warnings don't mean a thing in this part. Okay? You're like, okay, well, it's just warning. And it'll do something like that, and you don't need to post on Slack. This is fine. What this is interesting is, though, you can technically write your custom jars that wouldn't generate this warning, and it will. Okay, that error thing, just ignore. This is just our servers just being bad. Please, sorry about that. Okay, now you have a session. So you should have some kind of equals use should be non-zero. Some memory should be used. So right now, with this application that I just launched is running is using 305 gigabytes of RAM. That's a crap ton. Has 61 cores, and all these things kind of We're gonna explain what they are. So being the all omniscient, powerful user you are, you can click on the application and kill it. But it'll ask, are you sure? In this case, I'm not too sure, so I'm just gonna cancel it. But you can kill your Jupyter notebook by pressing Control-C here and like ending your Jupyter program within Jupyter. But actually, you can also kill your processes outside. Wait, did people miss PySpark? Okay. PySpark. So all you need to do is this. Oh, not that. Master, yarn, deploy mode, client. Sorry. Did everyone do that? Sorry, I kind of just glossed over this. So I'm telling Spark, or telling PySpark that, yo, you're the one designated to run Spark. So PySpark runs on yarn in the mode client. Is that good? Everyone good? Everyone got to that process? This is beautiful. Last time was like, oh my god, my computer died. This is good. Okay, is everyone good? Is everyone at the stage? Everyone ran? Okay. I'm going to assume yes. And you should be able to see the application. Okay. So, let me run something. So, what you can also do is click on Applications, and in the Tracking UI column, you should be able to see something called Application Master. Start your notebooks too, right? Wait, where are everyone? Where's everyone?
Just started a new notebook.
You started a new notebook.
And it showed up like a whole bar kind of thing with no master.
Yeah, that's fine. It's fine. You started, but no. Yeah, she has an empty Jupyter. So, but can you check your 8088?
Yes.
Does everyone see this? Yes.
I can't. I can't get to any of the Hadoop screens. I can open Spark and run it, but it doesn't.
Did you run Hadoop? Did you run Hadoop?
Yeah, I did the start all.
Oh, okay. You want to open that? Yep.
I created a new notebook, but I just can't find it in the application.
What was that?
It like won't show up in applications, even though like I started a new notebook.
refresh the page. Okay.
Okay, can you show me? Can you see this then?
Like I can see that page, I just can't see any application.
Okay. Okay. For the sake of everyone, for the speed of the demo, I'll just sort of move ahead, but I can help you individually. There you go. So that's cool. So if I click on Application Master, ta-da! I get Spark UI. So my Spark UI tells me nothing because I've done nothing. It does tell me, if I go to Environment, it does tell me what all the values it's using it. So it says, for example, I told Spark to run in FIFO mode. It's actually understood me and said Spark scheduler mode is running in FIFO. It also has like all the driver memory, executor memory all in sync. Okay, so let's actually try running it. Okay, so I'm gonna import some statements. This is just for you guys to see now. I'm going to read in a file called review.json. And just to give you an idea of what that kind of looks like, that review.json file is actually a 3.2 gigabytes of text. So not anything, like not images. This isn't your 720p movie. This is actually all text. So this is on your laptop. If you try to load this into your memory, it will probably freeze, and something will flicker, and then you'll have to power close. And that happened to me multiple times. This is the actual data set that Yelp team uses, or used. It's probably even bigger now. Probably like 5 gigs now. So today I'm going to show you an example of how to do a word count, a transformation. So basically, Spark is really, really good for pre-processing. Its machine learning libraries are getting better. So the speed of the machine learning libraries is getting better. So the ML libraries are quite useful as well. But the actual useful use of Spark is really in pre-processing. So I've just so for me to load data sets of size 3 gigabytes, it takes me around 20 seconds. Oh, 10. Sorry. So I just loaded a data set into the memory. Spark now has it. So Spark will now, I can do like a count operation. And
Is it already in RDD? Like
yes, it's actually made into a data frame. So in this case, we're using a data frame. Okay. So people always kind of tell me when I first show them that, they're like, on my Python, when I load a data set and I tell it, give me the number of rows, it like does it instantly, right? But Spark actually doesn't really know the real number of rows because you're working with an unknown large data set, and in order for you to be able to count. Sorry. So basically, Spark doesn't know anything about the data set. You're just feeding it the actual data set that's in distributed format, and you don't know how many rows there actually are. That makes sense? Okay. So we can see we actually have 4 million rows. So we have 4 million reviews. Each review has, on average, at least 100 to 200 words. So we have a crap ton of words. So we're going to do an operation on the words. So I'm going to select 2 columns, review ID and text, because that's all I care about. And then, okay, so the interesting thing is I've already done something, right? I've loaded the data set onto the system. So in the PySpark shell, if I go to jobs, I should now be able to see things, because I've done things. So what did I do? I did JSON, I've read in the JSON file, I did it twice, just because I wanted to show you guys again. And then I did a count operation. So let's look at the count operations. This is quite interesting. So, count operations, I click on the description, count. So this is one of the stages. So let me go back again. Each stage is basically a circle on the DAG. So basically, like I have a. Oh, sorry, this is messy. So on the DAG, I had a bunch of you know. So someone asked before why, you know, is the DAG so complicated? This is the most complicated it gets. One goes to 2 and then comes back. Right? Maybe the results of this matters to 2 nodes. Make sense? But basically, let's say this is a circle I draw before making a MapReduce shuffle. That is a stage. Does that make sense? So if I click on DAG visualization, it actually shows me a DAG. And see how it's very simple? It's not actually, it's basically like one directional. There's no like branching, crazy stuff. Basically, each box is the DAG. So basically, it in Spark, it says, okay, I just need to MapReduce this twice. Looking at my optimized DAG plan. But this is not what it looks like. What it also has is an event timeline, which we'll not go into this time. I'm going to look at count, and here is also a DAG visualization. But I can also actually look at event timeline, and the event timeline actually tells me what happened at each of the stages. Okay. So I'm going to time my operations, but you guys can already kind of cheat and see at the bottom that I've done it before. To count, so what am I doing? I'm actually doing 3 things. So when you get a bunch of text, so when you have a lot of reviews, in this case 3 million reviews, what do I need to do first? I need to count the words, right? I need to first tag the words into like separate. So if I have my name is Daewon, then you need to split that into my. It's like all these words. So you first separate them into individual words, and you do what's called a stop word removal. So like some things like